So we're just going to quickly look at your results for timing Gaussian elimination, as well as whatever it is that MATLAB does when you type in A/B. So Gaussian elimination for a system of size 1000 by 1000 will range anywhere from 2 or 3 seconds to 25. Okay. So that depends, of course, on the hardware everybody has. Then for 2000, there are some zeros. I guess this run just bombed. So anywhere from 33 to 600 seconds. Okay, so we went from 3 to 17 to 33 to 100 seconds. Then this was my bad. Sorry. It had multiple choice, I guess, as a so there are type of the questions you can have is multiple choice, and for some reason it did this. So there is some error, no memory, closed my MATLAB, unavailable, and so forth when you push the limits to 10,000. But some people, those that actually could push it through, it was on the between 10 and 20,000 seconds. Okay. Now let's see how things look like when they're actually optimized. This is a split second, let's put it that way, and sometimes into hundreds of splits. Then for 2000, we had somewhere on the order of 1x is an array. Well, it is an array, but I needed a time. Okay, so this is somewhere on the order of a second to 2 seconds. Then for 5000, we're pushing to up to 6 seconds. And x is an array, by the way, is not the time. It's
yeah, that was me. I meant by like after the x.
No. You're like, there are way too many to type in here. True story, there are way too many. I just needed the time, the elapsed time. This is what you, when you do it late at night. Yeah, one of the emails I got at 9, so I'm guessing you finished this very late. So x is an array, that's fine. So somewhere on the order, so this one didn't go through for some reason. It's on the order of 25 seconds. So we had not being able to solve it at all, or somewhere between like 15 to 20,000 seconds compared to 25. So one of the reasons why this is actually faster is that for anything larger, so typically larger than 1000, there are 2 reasons not to use Gaussian elimination. One is that it is slower, it's the slowest method. And second is that the round off error piles up. And we can actually, round off error, you can actually do it yourself to just see what the difference is between the true solution and the solution. Look, AX, what is the size of the AX minus B? It should be 0 or very close to 0. And you can actually, in all of these systems, see how it grows as you have a lot of equations. And that's because round off error and all of the errors that we have when we are storing numbers in computers, as well as adding them and subtracting them and multiplying them a lot of times, that's what piles up. So there's a lot of algorithms that improve on that. And one of the ways to actually improve on the time is to do iterative methods, which is what we started last time. Now, before we actually today go to the programming of that, I just want you kind of think, I want you to think about timing, and this is how we're going to do. So if I do something like this, I have A is some random array, and its size is, I'm going to put N is 100, it doesn't really matter, N by 1, and B is rand of N by 1. So if I do something like this, How many operations do I do here? I have operation of addition. Okay. How many do I do? 100. Okay. If this n goes to 1,000, 10,000, a million, that scales to 1,000, 10,000, a million. Now, if I also did this, I now also have 100 multiplications in addition to addition, right? So I have 100 pluses and 100 times operations, so 200 operations. It's still 2 times n, okay? N was 100, so this is 2 times n operations. Even if I add one more line, it's maybe 3 times n, so it grows linearly with n, okay? So we call this, there is n operation, 2n operations below. So the number of operations grows linearly with number of size of the array. This is what we call O of n. Okay? It doesn't matter if it's 2n, 3n, 4n plus 5. It's all on the order of n. So in terms of timing, you will see that on different hardware, you will see a pretty wide range, right? But we do see that everybody is grouped in certain areas. So maybe you see 3 to 25 seconds timing result for all of the possible hardware. But overall, it's the same sort of order of magnitude, and it grows. Okay. Now, what happens if I actually have this, and I gave myself a random matrix so now I have matrix n by n, and I also go to the second loop and I say B of ij is A of ij times 2 plus 7. How many operations do I have now? 2 per this line, and how many times do I repeat this line? N times n. For every I execute this loop, and I have n i's. Yes, it's n times n. So this is n squared. Okay. Below we have n square multiplications and additions. Well, technically one of each, so 2n squared. So this grows as a square of n. Okay? So this grows as a square of n. Number of operations scales as O of n squared. Again, whether it's 2 times n squared, 3 times n squared, 4 times n squared plus 3 operations, that's all similar, really. This is how we gauge the complexity of algorithms and how long they take. So Gaussian elimination in itself is O of n cubed. And O of n cubed algorithms are bad. Okay? So this is why we actually in LU decomposition. And the part that is O of n cubed in Gaussian elimination is forward elimination step. Okay. So that's the expensive part, which is why we try to minimize it in LU decomposition. We try to do it only once. Okay, then we're done with it, and then back substitution and forward elimination are O of n squared, so that is cheaper. However, the cheapest is actually to do iterative methods, which is the topic that we started last time. So this was the timing on my computer. It pretty much it was similar to what you got. So this was the timing for the operator a/b, and this is the Gaussian elimination that we programmed. So this is going to be the case many times. What you'll learn in class is the basic method, and it's supposed to improve your understanding and how you do you understand what the methods are about. More likely than not, there was some more work done on these introductory methods, so to speak, and they have been heavily optimized, so software will perform a little better. But it is still important to understand how things work. Okay, so we are now going to back to our Jacobi method. So just a quick review, the way Jacobi method works. It's an iterative method, so we're going to start with a good guess and iterate. Okay? So if I start with my starting point, whether I refer to it as x0, x1, doesn't matter. This is now the entire vector. And we basically transformed an original array, original set of equations as follows. I basically expressed x1 from this equation, and this is what it is. It's b1 minus this sum divided by a11. Then I expressed x2 from this equation. This is what we get. x3 expressed is this, and x4. If I had more equations, obviously I would get the same. General formula from this previous step, so these are x's from the previous steps, such as k is equal to 1 here. So these are my previous x's. I basically compute this sum, which is multiplying this entire row of matrix with column vector x, except for that 1 term. So I'm going from j is equal to 1 to n, except when j is equal to I, aij, xj. So I'm trying to avoid that aii term here, right? So essentially this is the sum to xk, and then I say bi minus this sum after I computed and divide it all by aii. And I have to do that for every n. And I'm going to loop around. So basically I start with an initial vector as a guess, and then I compute the next vector, entire vector, in a for loop. And then I also iterate in a loop, while loop, until when? Until my error is small enough between the two guesses. Okay? And that can be done different ways. You can simply look at the absolute values between all of the elements that should be limited by that. So this is the example we did by hand last time. I hope you still have those notes. I would like you now pretty much to, so again, we're going to converge when my error is less than some tolerance. So you can look at the relative error or absolute error for every element of those vectors. You can also compute the norm of two vectors. That would be a fast way to do. So let's actually do that. Let's create function JacobiIteration.m right now in class. That function takes a, b, and an initial guess vector, and tolerance TOL, and performs Jacobi iteration. And I want you to test this method on this system. And this is the formula. And you can also, this is a little tweak. want you to let x0 to be an optional input using that n argn